All right, a bit on collisions. Now I gotta get a wireless lapel mic for this stuff, but we'll do a little bit on the board, a little bit here. Just want to kind of tie it all together, right? So if you remember from, I look like I'm Blue's Clues here or something. If you remember from the impulse discussions, when two objects collide, they apply an equal and opposite force on one another, right? So we have object 1 and object 2, all right? When they hit, all right, so when they hit, object 2 applies a force on object 1, object 1 applies a force on object 2. All right, that force versus time graph, let's see, that force versus time graph is going to look something like this, right, for that collision, where the area under the curve equals a change in momentum. All right, now that impulse that's given to each object has the same magnitude of each object, but in opposite directions. So if this car is moving in the positive direction, its impulse is in the negative direction. Right? So because when they collide, that force on cart 1 due to 2, or whatever way I'm looking at this, on 1 due to 2, right, that force is in the negative direction. So the impulse is in the negative direction. The force of 2 on 1, or I guess it's 1 on 2, all right, force of 1 on 2 is in the positive direction, so this one's impulse is in the positive direction. Because it's the same magnitude of force, acting for the same amount of time, they both experience the same impulse, however, in opposite directions. So that means the total momentum of the system before the collision has to equal the total momentum after the collision. Because, again, force times time is change in momentum. If this one's momentum change is negative 10 Newton seconds, this one's momentum change is positive 10 Newton seconds. The net change in momentum of the system being these two carts, the net change in momentum of the whole system is 0. Right? Therefore, if the net change in momentum is 0, well then the total momentum that exists before the collision has to equal the total momentum after the collision. Momentum is a vector quantity, right? So, all right, there's a couple ways to write this. Up on the regions, they just wrote P before equals P after, right? Where P represents basically the sum of all the little masses times velocities, right? The momentum, the total momentum here is the sum of all the little masses and velocities products, right? This is a vector quantity. P total, right? Sum all of the momentums. So this often ends up looking like M1 V1 plus M2 V2 equals M1 V1 plus M2 V2. I really hate having to write out all the subscripts on this, like before and after. Sometimes we'll do mass A and mass B letters for the names of the masses, and then 1 and 2 to mean like the time before, the time after. So I don't know. I just keep it organized, right? Here's the total momentum after, here's the total momentum before. The sign on the velocity, the direction of velocity dictates the direction of momentum, right? So these are easy problems to solve as long as you're organized. So my favorite one is always when one's at rest and they're equal masses, and I send one in. So let's say the momentum of this one is mv, positive mv. So that's the total momentum before the collision is positive mv. Well, the total momentum after the collision has to be positive mv. So when we let it go, this one's velocity basically just gets given to this one. This one stops. It gives all its momentum to. This one gives all its momentum to the one that was initially at rest. And then from there, we look at all different possible combinations, right? We like to make predictions, right? So I'm gonna start with the light one at rest, lower mass one at rest, higher mass one moving. When they collide, what's going to happen? All right, they're going to apply an equal and opposite force to each other. That force is going to have a bigger impact on this one because its mass is less. Acceleration equals force over mass. So this one's going to have a bigger change in velocity than this one. All right? So if I send it in, that one really takes off. This one loses some velocity. This one loses momentum. This one gains that momentum it lost. So the total momentum of the system remains constant. It's fun to start with the heavier one at rest, right? What's going to happen here? So this one's going to come in, they're going to hit. That force is going to act on both of them. All right, the force is going to act on both of them. It's going to have a bigger change of velocity on the lighter one. So is that going to, what's that going to do? Is it going to just make it stop? Is it going to bounce backwards? What's going to happen? Well, that can kind of depend on how fast it's going initially, right? So in most of the cases, it just rebounds, right? This one goes away slow. This one rebounds pretty quickly. Right? It rebounds slower than when it came in, though. It has to. It has to rebound slower than coming in because this is all the momentum right here, right? Think about it in magnitude, right? This one has to bounce back slower because if it bounced back at the same velocity, then, what would be going on over here? It can't. It's losing momentum, bouncing backwards, giving that momentum to this one, right? So positive momentum, negative momentum. So after the collision, these two momentums add up to equal whatever this initial momentum was. Now the other types of collisions, these are called elastic collisions. Anytime, no, I shouldn't say that. Elastic collisions are ones in which total kinetic energy is conserved. We're not going to look at that yet. We will later on once we do energy. Inelastic collisions are when energy is not conserved. These collisions are inelastic. None of the collisions we do in class are elastic. It comes close, right, because they're magnets, but there's still always an energy loss. The ones that are definitely, sometimes people call these elastic because they bounce off each other. That's not accurate. That's not really accurate. The only way to tell something's elastic is if the total kinetic energy is conserved. This one here, the other fun way to do this is to take these and have them stick together. Now, let me see if I have the right Velcro combination here. I just noticed that one of these needs a different piece of Velcro on it, which I don't appear to have. But that's okay. I think they'll stick together. So, inelastic collision is when they stick together and slide away. So the total momentum is in the incoming one. This one has the same mass. So in effect, you are doubling the mass of the moving object, so you half the velocity. The velocity slows down to 1/2 of what it was. Now, some things happen when you try to make one of them heavier, right? This one's got the momentum. It slows down, but not as much. You're not doubling the mass. You're only increasing the mass by 1/3. Therefore, the velocity only goes down by 1/3. Another type of collision, it's almost like a collision in reverse, is if you trigger the spring between these, right? There's a spring system, right? It's like an explosion. The momentum starts off at 0, all right, total momentum starts off at 0, so then the total momentum afterwards must be 0. So if the total momentum afterwards has to be 0, then these two must add up to have no momentum, right? So whatever negative momentum this one has the same positive one. So they're the same mass, they go away at the same speed. Now, that's not the case when you make one heavier, right? So let's say I'm going to make this one heavier now. I'm going to try to trigger the trigger there. The mass is nice to use to trigger it, but I'll try to use this little piece of plastic to trigger it. If you use your finger, it messes up everything. It doesn't really work that well. Your finger causes the cart to get caught up. So use this little piece of plastic. Now, this one's heavier, right? So the prediction is that this one will move back slower than this one moves forward, right? So pretty dramatic, right? So the MV, this MV plus this MV must equal 0. So this one's negative M times the negative V, M times the positive V. So it's 5 times the mass. This one's going to have 5 times the velocity. All right. So that's called recoil, right? This one recoils. Usually the one that goes back slower, you say recoils. It's like if two things collide, well, which one's recoiling? Well, both of them are. Well, yeah. Usually the way we think about it is the more massive one deflects the lighter one, and the more massive one recoils, changes the path of the lighter one. Recoil speed is an important thing in various nuclear physics, high energy physics applications, the recoil speed of the nucleus. In fact, pretty cool thing, conservation momentum. When a nucleus undergoes fission and shoots out radioactive particles, it has to recoil because of momentum. Even if it shoots out light, it can recoil because it's shooting out energy, which is basically mass. Like by light, I mean gamma rays or whatever. The nucleus that's decaying will recoil. Pretty cool. It actually, by shooting out a photon, which is virtual mass, at a high velocity, the nucleus of the atom actually recoils in a radioactive decay. It's pretty cool thing, but it's physics, it works. When a positron and an electron meet, right, they hit each other and disintegrate, it always sends out 2 photons. So PET scan, positron emission tomography, you know anybody that works in radiology or anything like that? And a PET scan, you introduce a particle that gives off beta minus particles, and which are positron or beta plus particles, which are positrons, beta plus decay, I should say, gives off positrons. And you put this inside the body, and the fluid travels, it's decaying, and when that positron comes off, it almost immediately hits an electron, because you're filled with electrons, you've got trillions and trillions of electrons in you, and that positron hits the electron and gets converted to gamma ray radiation. Is it gamma ray or is it KUVs? I forget. It gets converted into a photon. Now, when they collide, those two things, it gets converted into energy via E equals mc squared, basically, you know, and it shoots out 2 photons from inside your body. So it's like an X-ray, it shoots radiation through you onto a screen, and a positron emission tomography is shooting the radiation out from inside you and then hitting a detector. And depending on the time delay and the energy at which they hit the detector, you can figure out the density of the materials that those gamma rays or that radiation, that photon travel through. You know, you figure out where it came from, figure out what the density of the tissue is around it, and you can create an image of that. It's like an X-ray from the inside out. It creates a 3-dimensional image, actually, rather than a 2-dimensional image, which is really cool. MRI, same thing. You get your magnetic poles aligned in the hydrogen atoms in your body, and you hit them with a burst burst of radioactive radiation via radio waves, actually, and it causes that magnetic pole to move, and then go back. It goes back. It gives off radiation. Different thing here, but in the positron emission topography, they go in exactly opposite directions because of conservation of momentum. So that helps you really figure out where the particle is located and what kind of stuff it went through. But pretty cool. The mathematics are very easy. You just literally set this up. Be careful in these problems, that are these practice problems, right? M1, V1 plus M2. You gotta be careful with the signs. I encourage you to make a drawing, label them. You know, whatever way you set up the coordinate system, you just roll with it and use it that way. All right? Anyhow, I gotta get going. I'm on lunch duty here with Mr. Roach. I didn't hear the bell, but it should be ringing any second. Talk to you later.